And this leads us to district energy, which is really, I would say, an enabler of all the technologies that we have discussed here. And the reason why I phrase it as that is that when I read about district energy talked about in the news, for example, it's a lot of the times misunderstood and lumped into the same category as an energy source technology like geo or biomass or waste. It's not a source, it's a distribution system. So I think we're very familiar with electrical systems compared to thermal systems, but district energy is essentially a grid, but it's not the power plant. It's going to move the heating energy from A to B, but it doesn't make it happen. So this is where sometimes it gets a little bit confused. So this is just a really simple diagram of what a district energy system is. It's typically a large network, small depending if you're getting started, of buried pipes where we're sending, they have to come in pairs essentially. So we're going to send out hot water, and then that building is going to absorb that heat out of the hot water and return back cooler water to be reheated again at the central plant, and then just rinse repeat. This is essentially how a building heating system works. It's just we're taking it from the building and scaling it up to an entire neighborhood and entire cities in some examples. If we want to do heating and cooling, then we just double the system. So now we go from a 2-pipe system to a 4-pipe system. And you might hear them referred to that, for example, as this is a 2 or a 4-pipe system. District energy is much more common in North America than people realize. A lot of people think of it like, oh, this is like a European infrastructure. I've even had people call it, oh, that's Soviet heating systems. I thought that was a good one. But most of us who went to post-secondary education, our lecture halls were heated with this infrastructure, and nobody just knows or talks about it. So there's tons of district energy systems across Canada and the United States. We just do a really good or poor job of talking about them, to be honest. You might also hear district energy systems talked about in terms of generations, like, oh, this is a 1st gen or a 2nd gen or a 5th gen or something like that. And you might be like, what the heck does that mean? So this is the best kind of way to explain it. So 1st gen, as you can imagine, was the OG, the original of district energy. And we are combusting back, in the 70s, 80s, and 90s, fossil fuels, coal, natural gas, fuel oil in some cases, typically in a power plant for combined heat and power, and we're generating steam to turn a turbine. Then we just take that steam also, and we can then push it into a district heating system. And so we have a steam district heating system. When we go from a 1st to a 2nd generation system, we're ditching the steam and replacing it with hot water. So we're going to get up to 100 degrees Celsius on the maximum. And then once we get to 3rd and 4th generations, we're just basically lowering that temperature profile. So instead of supplying at 100, we might be in the 80s or 90s for 3rd gen, and we're basically at domestic hot water temperatures for 4th gen. So in the 60s Celsius, for example. And as you can see here, and I'm going to hang on to 5th gen for a second, put that aside for a second. And then you can see on the curve here, as we lower the temperature of that system, the efficiency increases. And you might think, oh, that's awesome, that's better. And you're right. But that is, I would say, a minor advantage of going to the lower temperatures. The greatest advantage of having a lower temperature district heating system is it makes it more economical to access renewable sources of heat. So if you go back to a 1st gen system and we have to generate steam, we need temperatures well above 100 degrees Celsius in order to generate steam on a consistent basis. The list of things that we can do to get that is pretty short compared to the list of things that I can use in my toolbox, so to speak, to get water up to 60, 65. So bringing that temperature down, yes, increases efficiency, but the greatest advantage is that it makes it more feasible for us to put renewables into the mix. And what I mean by mix is that district energy is a completely fuel neutral form of energy distribution. So, water here doesn't care what makes it hot or cold. It doesn't care. It doesn't have an opinion. So if you have a district heating system, then, and maybe it was started on a fossil fuel power plant, you could build a biomass plant in another location, or a big wastewater energy exchange heat pump system in another location, and you can connect it into these district energy systems and start to displace the fossil fuel out of the equation. And you won't have to change a single pipe in the ground because the water doesn't care what makes it hot. So it is the ultimate form of kind of future-proof thermal infrastructure. So when we get into 5th gen, this is where things get really interesting and kind of more complicated. So I'm going to try and keep it really simple. But the 5th gen system is sometimes called an ambient system, but we're not just incrementally lowering the temperature when we go from a 4th to the 5th, we're dropping it to the floor. We're going from like 60, 65 degrees Celsius to anywhere between like 0 and 30 degrees Celsius. And I give a range because instead of a more stable temperature going to the building, we have a much more dynamic system. The system's temperature is going to change based off of the season and based off of the needs of the system. So it's a much more complicated system, but it's a much more adaptable system when designed properly. Because we're at this 0 to 30 degrees Celsius range, the other big difference between generations 1 through 4 versus a 5th gen system is I have to have a heat pump now. So 1 through 4, we are directly supplying heat to the building. We do not need any other technology like a heat pump. 65, even at the 4th gen, is going to be able to directly supply the temperatures we need to do domestic hot water. And your thermostat, it sure as heck isn't 65. So we absolutely have enough temperature in order to get the space heating load that we want. But when we're dealing with an ambient system, we're going to need a heat pump to enable getting to the temperatures that we need to see inside those buildings. This is just a quick kind of table to summarize this. So great examples of steam systems are, New York has a very famous steam system. Same with Toronto, York University here. This is a very short list. It's much longer in reality. We get into the next generation. There's still somewhat older campuses. N-Wave in Toronto has a steam and a hot water system. You can kind of tell the eras that they were built in based off the temperature. Then we get into 3rd gen systems. Hamilton has a 3rd gen system, St. Paul, Minnesota, and there's tons of these now in Scandinavia. Then we get into 4th gen. These are less common in terms of the traditional building stock of district energy here. But ZB built one just recently that we helped them design. Princeton University is a great example. And then we get into 5th gen, and we're seeing these a lot more. ZB has 2 systems. That's a whole other webinar for another day. But Okotoks is a great example. And then there's those separate district cooling systems. So Toronto has a separate district cooling system. And you'll see these obviously more prevalent the further south we go across North America. So back to this diagram, this is typically what a 1 to 4 generation system looks like. But this is what a 5th generation system can look like. And so this is an ambient distribution system, district energy system, and we're able to pick up not one bore field, but multiple bore fields that are both serving the building built above it, but are also able to interact with the district ambient system, which then also allows us to pick up trunk sewers. So we did a really great conceptual design activity for a project in the West End. I can't name it for NDA purposes, but it was a massive, and it will be a massive real estate project with multiple phases. And we were able to deliver a concept that made financial sense, where the first few phases had geosystems that were able to support the buildings by themselves. And about the midway through the development, it made sense to then put in the ambient district energy system so that we could capture a large trunk sewer on the perimeter of the building site. And then that allowed us to then backfeed and complement the geo infrastructure that was already designed, built, and operating, and allowed us to then build or serve the energy needs for the last 2 phases with minimal additional energy infrastructure, essentially, to the point where the last building didn't have any geo or any of its own infrastructure. It was basically just like a district heating customer, just had a heat exchanger to send and receive heat to and from the system. So these are the advantages of these types of systems.
And just so you understand, in terms of what makes fifth generation different from the previous generations, one, it would be low carbon or no carbon, but also it has a lot more complexity in terms of different sources coming into it. And it's not just a one kind of stop shop in terms of the inputs that go into the system to provide the heating and cooling requirements. It would be using a variety of different sources to meet the collective need. Is that correct?
Yes, 100%. And there's massive pros and cons associated with this. As I keep saying, there's no free lunch. Like if there was just a slam dunk, we should just be doing X, like Rathco wouldn't exist. So there's a challenge and an opportunity. It's a real philosophical thing about dualism we're dealing with here. But all of that optionality creates complexity. All of that access to different types of sources means there's more human beings and stakeholders we have to get involved. So there's absolutely pros and cons to this type of approach. The other thing that's important to mention is that existing buildings, because they were designed and built in an era of like ludicrously cheap natural gas, they resulted in the industry building high temperature heating systems because they had natural gas boilers that they could just flick with a switch, turns on within a minute, and you get like really hot temperatures really quickly. And so the rest of the building's heating systems designed basically around the performance of that technology. That technology does not retrofit cost effectively down to really low temperature stuff.
Right.
And so we're seeing the ambient go into a lot of new projects, but the retrofit market is just starting to take companies like mine seriously to look at like what does this actually mean if we want to decarbonize it. And as you can imagine, it's a much greater challenge than doing it with a new construction. New construction, my personal opinion is with the way things are going, I think it's going to be a stranded asset if you do anything that's not renewable. But retrofits is a whole other ballgame in terms of strategies to deliver cost-effective solutions.
Perfect. Thank you.
And then this is kind of like the wrap-up slide here. I know we covered a lot of stuff, apologies, but there is a lot of stuff. But this is just to inspire everybody. This goes my entire career I've spent working in infrastructure, basically in buildings that don't require human beings to live in. They're buildings for equipment. And I always saw it as a missed opportunity for architects because, again, humans get in the way of a lot of things. And it's true in architecture. Like you need balconies and you need emergency exits and egress routes and all the views. Well, a pump system and a heat pump system and whatever, they don't need any of that stuff. And so from an architectural perspective, you can do a lot of things with a central utility plant building that you can only dream about doing for a residential building. And so here's some really great inspirational projects. These are not renderings. These are real power plants, district heating power plants, all in Europe, unfortunately, but they seem to be interested in making their infrastructure beautiful in addition to just functional. And I'll just focus on one in the top center here. This is Copenhagen, as they call it. And this is one of the world's largest energy from waste facilities. So there are no landfills in Denmark. All of the waste goes to these energy from waste facilities where the waste is incinerated, but the filters on these systems now are so good. This is not the 1980s anymore, that the emissions coming out of these systems are cleaner than like a diesel truck exhaust pipe. So this is a really clean facility. They've also enhanced the performance of this facility with heat pumps. So they're actually able at certain times of the year to get efficiencies above 100% by using the heat pumps. And in true Danish fashion, they said, well, let's make this a playground as well. So they built an artificial ski hill on top, as well as the world's tallest outdoor climbing wall. So you wouldn't even know that there's huge amounts of garbage going into the underside while you're enjoying a miniature ski holiday. So it's a great inspirational example. And they actually built this. Like this is not, you can go there and buy a lift ticket. So this is not theoretical. So this is me just trying to inspire everybody to say, hey, infrastructure can be beautiful in addition to functional.